Hey guys, in this video I want to show you the pathfinding algorithm I implemented in Unity. This is the shortest path algorithm from source to destination. It uses BFS search instead of A star or traditional Dijkstra algorithm, and that's because in an unweighted or equally weighted graph, the BFS search and the Dijkstra algorithm results in the same path. So it's the same uh, algorithm implementation wise. Now, to achieve graph traversal algorithm in a canvas like this, what I have done is divided the game canvas into multiple grids, and each grid would be a node of the graph. As you can see, the canvas is divided into grids like this. This works because consider a red color ball in between the grid. Its neighbors would be the blue color arrows. Similarly, if the ball was in one of the node of a graph, like a traditional graph, which we are very used to, then the neighbors would be represented through the edges, and the same neighbors can be represented through the blue edges too of the grid. So the graph and grid are implicit conversions between themselves. You can find the four directions using a direction vector and add it to the four sides if there is a four direction movement uh, game. And you can check for grid out matrix out of bound for like valid neighbors. So using this implicit conversion technique, you can like convert any graph algorithm into the grid algorithms and apply them to find the necessary needs. Okay, next I would show the demo of how the project looks like. Currently, I have like four bricks, which imply those are four walls. I am the player starting at the origin 0, 0, 0, 0, 0. Now, wherever I click on, that will be the destination point for the player to find the shortest path to. So, suppose I click here, yeah, it finds the shortest path to there. I've made sure the green objects disappear after 1 second to prevent cluttering of game objects in Unity. Now, suppose I remove one of the walls here, either this or this, and try to apply the BFS algorithm. As you can see, it found out the shortest path after removing the walls from this side instead of going from here. So the algorithm actually works. You can place walls too using like the right mouse button now. And so yeah, if I place a wall here and try to find, yeah, instead of going through this, it goes through this. So the shortest path is being found. I want to just do a brief overview of the code implementation and go through a detailed tutorial in another video if the people want it. I have a grid class here, not the mono behavior class, the plain C# class that stores information for height, width, and all that, the origin and all that. And it acts a 2D matrix, grid matrix, and to store the text objects, I create another 2D. The way we traverse a 2D matrix is like, yeah, from top to bottom and left to right. Whereas Unity's coordinate system moves from left to right and bottom to top. So to convert between the two systems, I have some functions that will just invert the coordinates so that we can place those walls and then traverse to the grids of the Unity world easily. This function just creates those boxes and then creates the text object and places it inside those boxes. The function responsible for creating the text is this function. All it does is create a game object and add a text mesh component, and then to that text mesh it gives some properties like character size and font size and all that. Yeah, this is another function to convert between directly from the Unity world to the matrix C# matrix representation so that I can place them easily. This is the pathfinding class, not a mono behavior class, just a normal class. Main things are it uses a 2D visited matrix and is walkable matrix. The visited matrix represents paths which have been already explored if it's true, the grid cells, and the is walkable matrix represents grid cells which don't have a wall in them if they are true. The direction vectors di and dj represent the four ways a character can walk through in the game. Those are north, south, east, and west. The queue shown here tracks the points to be explored. Instead of wrapping them in a single object like something like node x comma y with x comma y as members, I separated them out into two components so that it's faster without object wrapping and dewrapping. I initialize both the matrices, the parents matrices as -1 comma -1, indicating that the parent of each node initially is itself. Then initialize all cells as walkable cells in the grid. The find wall function finds all the walls in the game world and makes the respective grid cells not walkable. In the BFS function, I visit the starting vertex passed in and add it to the to be explored, whose vertex to whose neighbors has to be explored. Then while there are members in the queue, what I do is like grab each one out of that and check if that's the ending vertex. If it's so, break through that, or else explore its neighbors. While exploring its neighbor, I pass through all the north, south, east, west direction, check if they are valid. If not, I break out of the loop and I break out of the function. And if they're valid, I add them to the to be explored a queue and visit that so that it's not explored by multiple parents simultaneously. And make the parent of the neighbor as the one that called it. In the print path, I iteratively go through the each nodes and check if the destination node parent is -1 for -1. If so, that means I have reached the parent. Or else something similar to path compression. What I do is like find the parent of the current node by adding it to the a string which stores the parents. That string looks something like this. Since my destination was 6 comma 18, then I went through the parents of 6 comma 18, and the thing that called 6 comma 18 was 6 comma 17. Similarly, this happens until I reach 0 comma 0, which was the starting node, and since this doesn't have any parent, it stops there, comes out of the while loop and prints the path. So that's it for the code. If you want a deep tutorial on this, please comment it through. I'll post one. Thank you.